everyone. We're the Autumn 2024 Data Science Clinic team for CMAP. We're excited to present our work on our project this quarter, expanding stormwater infrastructure data for climate resilience. I'm Anna, joined by my teammates Collin, Mohit, and Xiaoyue Wei. We've partnered with the Chicago Metropolitan Agency for Planning, also known as CMAP. They are the regional planning agency for northeastern Illinois, focused on sustainable growth and resilience. And their mission is to drive innovation, foster collaboration, and advance a shared vision for an inclusive and prosperous region. Of CMAP's core goals, our project contributes to addressing climate change by enhancing resilience and protecting natural and water resources. Climate change is putting the Midwest at high risk, according to the U.S. EPA. The negative effects of climate change may manifest in the form of flooding, erosion, and reduced water quality and availability. Stormwater storage systems, such as the detention basin shown on the right, help mitigate these risks by holding excess rainfall and runoff. CMAP is establishing northeastern Illinois' first comprehensive stormwater infrastructure inventory, directly supporting their objective of regional climate adaptation and water resource preservation. This inventory will enhance regional flood prevention and erosion mitigation capabilities, as well as support data-driven decision-making for stormwater resource management and resilience planning. To support CMAP, we are developing a deep learning model trained on labeled stormwater storage data from Kane County. This model enables us to predict and identify stormwater infrastructure in regions without an inventory, such as Cook County. By creating a scalable solution, we aim to support resource-intensive manual survey methods, improving efficiency in building the inventory. Ultimately, this model could be used to build stormwater storage system inventories in other areas beyond northeastern Illinois.
The model uses two datasets to classify stormwater infrastructure: the Natural Agriculture Imagery Program dataset, or the NAIP data, provides area imagery covering the entire United States. Second, we are leveraging the Kane County dataset, which contains a comprehensive inventory of stormwater storage facilities. This dataset identifies various types of stormwater infrastructures, which are assigned to a distinct label. Our deep learning model classifies 4 basin types, and each of these serves a different purpose in the stormwater storage system: pond, mesic prairie, turf, wetland, and an additional background class. These basin types have unique qualities regarding water retention, infiltration, and filtration. Understanding these differences help optimize stormwater management or flood control, water quality, and ecosystem health. Our project's final deliverable is a deep learning model that can identify stormwater storage infrastructures and their basin types. As seen in the image, the model will process NAIP images and output predictions that identify different basin types, which are essential components of stormwater management system. Our model is first trained on samples of area images, along with the overlay that identifies certain portion of the image as different types of infrastructure. The model then attempts to identify the pixels that match stormwater infrastructure classes on new images. We measure model performance using the intersection over union. This measures the overlap between the predicted pixels and the areas actually labeled with corresponding class. IOE values range from 0 to 1, where 1 indicates the perfect alignment between the predicted areas and the corresponding ground truth label. Model setting tuning involves finding the best configuration for the machine learning model, such as batch size or learning rate. Manual tuning is slow and inconsistent, so we integrated an external framework to automate the process. This framework uses past results to predict promising configuration while balancing exploration of new settings with refinement of effective ones. By automating model setting tuning, we've made the process faster, more consistent, and scalable.
Automated model tuning significantly improved our model's performance. The baseline IOU had a 95% confidence interval of 40.7 to 61.9. After tuning, the IOU ranged from 49.2% to 69.6%, representing a 15.8% improvement in performance. A 95% confidence interval means that we can be 95% confident that the true performance of the model falls within this range. Statistical analysis confirms that this improvement is meaningful, highlighting the effectiveness of our tuning process in enhancing model accuracy. The model sometimes misclassifies rivers as ponds, since ponds can look visually similar to those other bodies of water. The model lacked river-specific data to help it differentiate between ponds, rivers, and streams. To address this, we incorporated river and stream data into the model. However, river objects are too large to feed to it directly. In this visualization, we can see that some of the rivers span the entire county, with some of the largest rectangles accounting for many miles of aerial data. We created small chips that cover each river segment to feed to the model, each one now only covering a fraction of a square mile. This allows the entire river to be processed piece by piece. The visualization now shows small rectangles that cover the river in more detail. Once debugging is complete, the model will use the river data to better differentiate rivers from ponds. This will reduce classification errors in areas with complex waterway systems and ultimately provide a more accurate foundation for waterway mapping and analysis. A digital elevation model is a 3D representation of the Earth's surface where each point shows the elevation of the terrain. On the left, we can see an image that has a portion of a wetland. In the DEM image, we can see that the area colored the darkest of blue corresponds to the wetland, indicating that the lowest depths of the ground are located there. We have successfully implemented a DEM class that generates clips that correspond to identical Kane County image data. The height information can inform the location of depressions in the image, which can help the model identify different stormwater storage types. We add the corresponding DEM image to each sample image to begin processing the data. We then normalize the samples to ensure consistent value ranges between 0 and 1. Data augmentations are techniques that strategically transform existing training data to techniques like image flipping to artificially expand datasets, prevent overfitting, and enhance machine learning models' ability to generalize across diverse scenarios with limited original data. We had to adjust the augmentations that were being applied to the RGB image to ensure that the same augmentations were not being applied to the DEM dataset, and to ensure that the DEM dataset was being processed properly. While no improvements were observed in training and test performance, further work can be done to improve DEM processing and to tune the model.
Using the raw DEM data, we perform fill analysis. Fill analysis is the process of adjusting gaps or missing elevation values in the DEM data by filling these points to match the lowest surrounding elevation level. DEMs often contain gaps or missing data, especially in low elevation regions, which can confuse models and lead to poor predictions. Fill analysis ensures smoother and more consistent turning data, helping models focus on meaningful turning patterns. In our approach, we applied fill analysis to the DEM data. We used the fill analyzed data to identify only the areas that originally had low elevation values by finding the difference between the original DEM and the fill analyzed DEM. As a result, we were able to generate a new DEM dataset that highlights only the filled areas. As seen in the right, the area shown in green indicates the filled areas. The darker shade indicates a lower elevation level. Moving forward, we need to test our model using the original and fill analyzed DEM to identify which dataset helps the model perform better. The model performs well during the training phase, but struggles to make accurate predictions on new data, which is a common challenge where a model fails to generalize beyond the patterns it learned during the training phase. To address this, we implemented dropout, a technique that randomly disables parts of the model during training. Dropout forces the model to learn broader and more general patterns instead of relying too heavily on the specific details from the training data. However, our initial results showed no improvement in the model's performance. In fact, higher dropout rates seem to reduce test accuracy even further. This suggests that dropout, at least in the configurations we tested, may not be the solution to improving the model's ability to generalize. We'll need to explore additional methods to address this challenge and help the model perform better on new data. Model tuning achieved a 15.8% increase in IOU over baseline performance, a significant improvement. Testing dropout was an important step in testing generalization techniques. The team was has almost fully integrated the river, DEM, and fill analysis datasets into the model. The main challenge with these data sources was processing, which is now nearly complete. This has laid the groundwork for future performance improvements. The river data implementation needs to be debugged before it will improve the model's accuracy. Additionally, we need to properly tune the model now that the DEM data has been incorporated. We also need to identify which of the original or fill analyzed DEM data helps the model perform better. Lastly, we suggest experimenting with additional generalization techniques to improve model performance. That concludes the presentation for the CMAP team. Thank you for your time and attention.